times the number of edges over 3, right? So
Right.
the way we can do that is by using indicator variables. So you can say that like our indicator variable is 1 if the edge is satisfied and 0 otherwise. And that's like, so that's the way that we go from one edge to all the edges.
Okay. Okay.
And then, so once we have our indicator variable, we can use a formula that's like the expectation satisfied edges equals E of the summation R for all the edges, which is essentially, since these are independent, we can do this. Where X is our indicator variable. Okay. So the probability of our indicator variable is a formula that we have, which is the probability at X equals 1. So the probability that X equals 1 is 2/3, right? Because the probability for an individual edge that it's satisfied is 2/3.
Yes. That's true. Yeah.
So that is what we can sub in for this, which means that we essentially are just doing a summation over all the edges of 2/3. So then you just get 2/3 times the number of edges.
Oh, I see now.
Yep. So that's really all you need for A. And then for C, you're going to use Markov. So what you're going to do is say probability that X is greater than A equals probability that X is less than E of X over A. So this is the Markov inequality. And the way you can leverage this, so if we are using, we're essentially trying to find the probability that at least half of our edges are satisfied, right? So if we're trying to find the probability which is also equivalent to right? Because if at least half our edges have to be satisfied, we're also trying to find the probability that at most half of our edges are unsatisfied. Which the reason that that is nice is because we can say 1 minus that minus our answer is going to be
Oh, because 1 is like 100. Okay.
Yeah. So what you're essentially trying to show is that we can find the probability that more than half of our edges are unsatisfied And then 1 minus that is going to be the probability that at most half our edges are unsatisfied. So find probability that the number of unsatisfied edges is greater than the number of edges over 2, right?
Mm-hmm.
So if we find that, we can do 1 minus that to get the probability that at least half our edges are satisfied.
Correct. Okay.
So in order to find this, let's say x is the number of unsatisfied edges. So we're looking for the probability that x is greater than e over 2, right? So if we make that our a, we can do that. Does that make sense? So the reason that we're making that a is so that we're finding this probability, which is the probability that the number of unsatisfied edges is going to be greater than e over 2. So you essentially choose the value of a that gives you the probability that you need.
Okay, I see that now.
Yeah, that's the kind of confusing part. But now that we have this, so what is e of x? We kind of solved in part A a little bit, is 2e over 3, right?
Yes.
But that was for the number of satisfied edges. Mm-hmm. So for the number of unsatisfied edges, it's going to be like
1/3.
Yeah, exactly. Because it's 1 minus the number of satisfied edges. So here, our e of x is e over 3, because again, we're calculating x as the number of unsatisfied edges.
Oh, okay.
So that's the expected number of unsatisfied edges, which is the place that some people trip up. So what we can do is less than e over 3, and instead of dividing by e over 2, we're going to multiply by 2 over e. So if you do this, our e's cancel, right? And we just get 2/3. So that's a probability that more than half our edges are unsatisfied, which means what's the probability that at least half our edges are satisfied?
Would be greater than 1/3, or do you like flip it?
Yeah.
Okay.
It's 1. So yeah. So the probability that it's at least half our edges are satisfied is 1/3. And that is the first part of C. And then you need to find an algorithm with some probability 1 minus epsilon that you have at least half your edges satisfied, right?
Right.
So in order to create that algorithm, do you have an idea of like what you would do? It's pretty simple. So essentially, it's something that we've done in I think lecture and recitation. We're just gonna run the same random coloring multiple times, and if we run this enough times, we know that one of those is going to be at least half of our edges satisfied with some probability. So in order to figure out what that how many times you need to run this algorithm, we want to figure out So the probability that we have some, one of our, let's say we run the algorithm n times, the probability that one of those times is, I guess, a good coloring, so one that fits our standards, is going to be 1 minus
Oh, to the power of n.
Okay, so the reason is for this is there's a problem for any time we run a random coloring, the probability that half our edges are satisfied is 1/3, right?
Right.
So the probability that less than half our edges are satisfied is 2/3.
Correct. Yes.
So if we run our algorithm n times, the probability that all of those times we have less than half our edges satisfied is 2/3 to the n.
Okay, I see that now. Yeah.
Yeah, so if we do 1 minus that, we're essentially finding the probability that that's not the case, that at least one of our trials, we do get at least half our edges satisfied.
Satisfied. Okay.
So you can set that to your 1 minus epsilon, and then the ones kind of cancel there, so you do then you solve for n. So if you use the log there, you can do and you can just leave your n as a fraction of logs, so like log epsilon over log 2/3.
Okay, perfect. Because I was looking at that math. Okay.
Yeah, that's all you need to do. And once you have that, you just say, okay, if I run my algorithm n times, I know at least one of those is going to have at least half our edges satisfied with a probability of 1 minus epsilon.
Ooh,
On this
okay.
equation here. So does that all make sense? I know it was a little quick. I'm just trying to get through it all.
Yeah, that helps a lot more because I was look honestly, I don't think I would have been able to figure that out on my own, but yeah, thank you so much for breaking it down for me.
Of course, and hopefully it's going to be similar enough to the future problems you can get it figured out. I think for all of these ones, I pretty much just give the answers in my office hours because like there's really no way to, if you haven't seen it before, to come up with it.
Mm-hmm.
So
I agree. Yeah. Okay. And do you have like any for like 2? That's the one I should just look up the lecture notes cache and then like read through that and like use that.
Yeah, I think it's going to be very similar to the lecture, but again, just focus on like when are we going to evict which blocks, and then like that being the case, what do we know? So right, like if we are bringing in k blocks, we know that we can't we're not evicting any of those blocks that we just brought in, right? Because we have k possible blocks to evict and we want to evict all the other ones first. And then if we have p that was brought in before our phase began, we're not going to evict p until the very last miss. So p is going to be in our cache until the last miss when the phase ends. And since we know that, we know that, I'm sorry. We're never going to miss on P because it's in the cache throughout the whole phase.
Mm-hmm.
That's really all you need for C, I think. But yeah, the rest of it, just everything we talked about, and take a look at those lecture notes to make sure you get. But for part